So hi Artyom, thank you for joining me in this interview. So today in your talk we saw the interplay of logic and combinatorics. And so could you please introduce a bit what kind of math you're interested in and this subject in particular?
Mm-hmm. Yeah, so logic is a subject which is based on foundations of mathematics with foundational questions like what is a set, what is provable, what is unprovable. But since our subject, model theory, since coming from these foundational questions originally, it has really evolved to a situation where somehow we are not as concerned about foundations anymore, but rather we're concerned about tame geometry and what things can be defined in classes of structures which satisfy some geometric restrictions, which rule out this Gödelian phenomenon in some explicit way. And the connection to combinatorics from my talk. This comes from some recent realization that even though model theory is largely an infinitary subject, so we usually care about infinite sets, infinite structures, but turns out that there are natural limiting procedures which allow to connect asymptotic questions. So for example, some quantitative question about a family of finite graphs. So for example, how many edges I have under some conditions. They allow us, there is a way to pass to a limit where somehow these quantitative questions get converted into qualitative questions about measure, dimensions, and things like this, where the infinitary methods of model theory can be applied and help us to extract this asymptotic quantitative information without somehow having to count anything at any point, which is what we very much like in model theory. We don't like to count, but if we can apply it like this, we are very happy.
And somehow this is an angle that is a bit different from the one that combinatorialists usually take to the questions, right? So somehow this helps in answering questions from combinatorics. And how did you come to this subject? What brought you to these questions?
Mm-hmm. Yes, so I started actually working in pure model theory somehow, which is mostly concerned with internal questions of the subject, where you're trying to study definable sets or the dual object types corresponding to the sets. And somehow we have a lot of methods and techniques which allow us to study these things. For example, in an algebraically closed field, just all the complex numbers, definable sets correspond to constructible sets. So things which can just be defined using polynomial equalities and inequalities. And what we do in model theory is somehow some kind of abstract, naive algebraic geometry. So we actually have points, but somehow without necessarily field being present in the picture. And the first time I really got interested in these combinatorial connections, it comes from the realization that some of the extremal combinatorial configurations, so for example, when we're interested in incidences, let's say between points and lines or points and curves more generally, or some other more general varieties, turns out that the extremal configurations, which witness the maximal possible, let's say, which show that some quantities are as large as possible, let's say. Turns out that they happen to be robust, and you cannot just pick it at random somehow. They actually tend to possess some algebraic structure in the background. And this is a theme which is very present in model theory. We have tools and techniques to recognize the presence of some algebraic structures, such as groups or fields, based on some generic information provided to us. So for example, someone gives me a trace of a group, so let's say an operation which somehow, there's no group a priori in the background, right? But I have some operation which, let's say, is associative with high probability somehow, whatever probability means in this case. Let's say on generic points on some variety, it's associative. And then we have techniques which allow us to actually find a group from which this operation has to come, okay? It turns out that these kind of quantitative questions, they correspond very closely to the themes of this trichotomy, Zilbert trichotomy, and Khrushchevsky group configurations, which are very central in model theory. So this realization that some particular counting questions, counting points on grids intersected with some varieties, they reflect precisely these central topics that we study in model theory. And so once somehow this was realized, originally through Khrushchevsky's observations, this becomes a very exciting thing to look at, because we have these infinitary methods, but turns out they can be applied to get some very concrete quantitative applications, which on the face of it don't mention model theory at all. And so somehow you're always happy when you can apply some, things and ideas from your subject to this other kind of questions. So that's what we're working to this somehow.
And in this exciting intersection of somehow model theory and other subjects, so what's something you would like to see proven in, say, the next 10 years, by you or by others?
Mm-hmm. Well, there's this Elikir-Szabó theorem, which was the topic of my talk. It's concerned with recognizing algebraic groups, more specifically abelian groups. So somehow we're given a definable set, or let's say for the sake of the conversation, let's just say we are working on the complex numbers. So we're just given some algebraic variety. Let's say I have an irreducible polynomial in some number of variables. And I'm looking at a zero set intersecting with grids of finite points, which get larger and larger and larger. And in the spirit of what I said earlier, that somehow extremal configurations often get witnessed by algebraic structures, turns out one can recognize that the only situation when this grid has as large intersections as possible asymptotically with my variety is when variety is actually essentially the graph of multiplication in some abelian algebraic group. And this abelianity condition, which was observed in connection to this problem in higher dimensions, at least by Hongguan, Bayes, and Brouillard, it's a bit restrictive because usually when one looks at this kind of problems, usually one hopes to find nilpotent structures rather than abelian somehow. This is witnessed, for example, by approximate subgroups. Deep theory developed starting with Khrushchevsky, then Green, Brouillard, Tao, and by now many other people. So it's a big industry. So one expects to recognize nilpotent structures rather than abelian structures. And somehow for this, we don't really have techniques yet. So there are some initial partial results, in particular carried out by some people here in Münster, which suggest that maybe it's possible to recognize nilpotent groups rather than abelian. That feels like it would be an ultimate theorem. And we don't really have techniques for that so far. So I think that's an exciting direction. And since there is some progress, but there's also realization coming with it that this would probably be difficult, that there's no some quick solution. So this would be very exciting to see. Hopefully it happens in the not too far away from us.
10 years.
In 10 years, in decade maybe. Yeah.
So also in the spirit of somehow this developments, say you meet a student and they're interested in the subject. So what is something they should certainly learn about? And what is some, maybe you've already mentioned, exciting new ideas that they should keep an eye on?
Mm-hmm. So I think I would also recommend, because my whole message here, right, that some ideas of stability from model theory somehow interact very beautifully with these combinatorial ideas. So I think I would have to give you a twofold answer, that somehow one should approach it from both sides. So on the model theory side, I think one could start with a fundamental theorem, Morley's categoricity theorem, which was a result which has on the face of it nothing to do with any geometry or counting. It's purely a question about what is definable and how precisely we can define mathematical objects in some restricted language. And under what conditions we can somehow define them as uniquely as possible, at least in fixed size, in fixed infinite cardinality. So this seems like a bit as a esoteric question which has nothing to do with anything concrete maybe. But it turns out that the proof of this result brought very beautiful structures to the center of model theoretic studies. Things like matroids arise very naturally. And the study of these matroids, which in particular cases boils down to actually studying projective geometries, or things like coordinatization of projective geometries by groups, all of the things are somehow hidden in there. So I would recommend learning a proof of this beautiful fundamental theorem, Morley's categoricity theorem, on the model theory side. And the combinatoric side, one should just start reading maybe the original paper of Elikir and Szabó, which I think is as good introduction to the subject as it gets. And maybe I will write a survey one day. For now, maybe it will happen eventually.
Okay, well, thank you very much for the interview.
Thank you, Simon.
Yeah, see you around.
Thank you.